GM guys, I'm Shafu. I'm gonna present Huff stackers today, which is a generator for stack comments. So yeah, I'm gonna go for 20 minutes, leave 10 minutes at the end for questions. If you have anything while I'm presenting, just put it in the chat and I will try to look at it. Okay, awesome. So yeah, Huff Stacker is a tool to generate these tag comments. So if you take a look at the README, let me put that into the chat. This is the input, basically a Huff file, right? And the output is a Huff file which with each line in a macro commented. And yeah, I think interesting would be to look at the actual implementation, right? So if you run it, you get the output with the comments, and the file that we use for this is this example. Just one thing which is important, this is definitely work in progress. There's still a lot of things which break this, and a couple of features which are unsupported. But yeah, if we look at the implementation, and yeah, guys, let me know if this is big enough. But I think it is. The API is super simple. So it takes in a path in, a path out. So the path in is the actual Huff file. The path out is the file which you're going to write into. And then it takes in a list of functions, right, which we will go into later, and a stack order. So the stack order is a flag for the CLI in order to determine, do you want to print the stack comments from left to right or right to left? The default is, as you can see here, is left to right. Okay, so let's hop into the actual parser and how the parsing works. What I realized is this is actually not parsing, it's lexing. And I didn't have to write my own lexer, which I realized like 2-3 days ago, because you can just use the one inside HuffRS. In the Huff repository, obviously there is a lexer because you need to compile this into bytecode. And yeah, one great refactoring would be actually, yeah, here it is in the to-dos, to replace the custom lexer that I wrote here with the lexer inside HuffRS. But yeah, how it works right now is we call this parse function, and the parse function takes in the file input, returns the contents, and then we parse out each macro. And just by the way, why do I call it function in the repo and not a macro? Because macro is a Rust keyword. So in your head, just replace the word function with the word macro. So let's take a look actually at the function itself. The function is a struct, or the macro is a struct, which has a name. The name of the macro, so if we take a look at macro Huff, this would be its name, set value. It has a start and an end, so the line number where the macro starts and ends. Each macro takes in a number of arguments and returns a number of arguments. In this case, it would be 2 and 0. It has a body, obviously. And where it gets interesting is a stack history. So what is a stack history? the stack history is, so if you take a look at the struct here, the stack history is a list of stacks, and each stack is a list of tokens. So why do we need a stack history? Because as you go through a macro, you actually need to keep track of the stack after every line. So if you take a look at the first line, 0x04, $0, $1 are the input parameters, so it takes 2. But after executing this opcode of pushing 0x04, this is the stack at this point in time. After doing this, after doing the next 0x04, this is the stack at this point in time. So this is why we need a stack history. For every line inside the macro, we have one stack, and each stack contains a number of tokens, right? What we can also look into is a token. So a token has a value, has a type. A token can be an opcode, but doesn't need to. And if it's an opcode and it takes an operands, it has a list of tokens which are its operands. Again, a great refactoring would be to just use the lexer from Huff or S, because it's a better implementation and it does all of this. So if you take a look, this is the lexer. It takes a number, it returns a number of tokens, and so on and so forth. But yeah, the current implementation has this token type thing, and the token types that we currently have are constant opcodes, a reference, a variable, a function, a return, a jump label, and an unknown token type. The most interesting of those is the opcode. So in the opcode struct, we have to know, obviously, its name, but we also need to know how many things it pops off the stack and pushes onto the stack. And we define those here. So for example, the stop opcode doesn't take anything from the stack and returns nothing. The add opcode pops up 2, returns 1, and so on and so forth. And we define this for every opcode, right? Okay. So we looked into the function, we looked into the stack, we looked into the stack history, and we looked into the token types. Now let's return to the actual parsing of the macro or the tokenization. So inside the parse function, we do we parse out each macro, and how the parse function works is actually very simple. So if you take a look at the right, we define a new function, and we basically iterate over every line inside the contents, right? And in order to determine if it's the start of the function, we just check does it start with macro start, and macro start is this defined macro, right? So inside the example, if we see something like this, define macro, it's the start of a macro definition. Okay, so this is the start of a function. The same for the end of the function. The end of the function is just the last curly braces, which goes close to the macro, and the rest is we are inside the function, and we just return the body of that function. So here you can see, we set the function, we've set the function body for each line. What we also do inside the start of the macro is we parse out its name. Parse function name is just a simple regex. And we get the takes and returns. This is also a simple regex. Again, there are definitely better ways to tokenize this. But for now it works. Okay, I'm already 10 minutes into this, so let me see if there are any questions. Yes, there are. This profile is recorded. It is recorded, yes. Okay. So once we parse out the function and we set the takes, the returns, and the name and its body, what we do next is we generate jump labels. And the jump label is something like this. In Huff, this is a jump label. So a string and semicolon, this is a jump label, and we need that. We need that in order to make jumps work. Actually, currently jumps are not supported, but generating this jump labels map, which we do here inside the jump labels, generate jump labels, will enable this functionality. And the jump labels thing is just a mapping between the jump name and the actual jump struct. Rather simple. Okay, so we do this for every function, and after we have every function, we iterate over all functions and generate its stack history. So inside function, there is a generate stack history. And this is, I think, where it gets interesting is, so the first thing we do is we initialize a new stack history, and then we initialize a new stack. And we initialize the stack by pushing in the takes parameters. So in this case, we would push $0, $1. Okay, this is just initializing it with the parameters it takes. Then what we do is we iterate over every line inside the function. If the function is not a comment, we get all the tokens in each line. Okay, so this is where the actual tokenization happens. And this is also how we support multiple opcodes per line. And then we iterate over every token inside the tokens list, and we do a simple match. So if the token is a constant, or a reference, or a variable, we don't have to do anything, we just push it onto the stack. So for example, 0x04 would be a constant, and we would just push that onto the stack without doing anything else. Then we have a function. So this, for example, would be underscore funcsig would be a function, or let's do this. This is better because funcsig is actually a built-in Huff function. Underscore xxx, which calls this function here down below. And how we execute the function is we look at the function's parameters. So this function takes in one of the stack and returns one, and this is what you can see here. So how I denote that is I just put in the name of the macro, and it returns parameter. I just increment it by 1. So if this function was returning 2, it would be xxx %0 and xxx %1, and so on. This is how I denote that. Okay, so this is how I execute the function, and if it's an opcode, I set the operands. I set the operands for each opcode, because if I have the operands, I can do some nice things when I print out the stack. For example, what you can see here, right? Or here, like this smaller, greater thing and stuff. And this is only possible because I know the operands of the greater than operation. And we have an execute opcode, which actually executes the opcode itself. So if we take a look at execute opcode, it's very simple. It just gets inside the token, we return its opcode, and then for the number of pops or a number of parameters it pops of the stack, we call self.pop, because remember we are currently inside the stack. And actually, which is an interesting fact, is there's no EVM opcode which pushes more than one operation onto the stack. So we just check, okay, if the opcode pushes something, we could have done this as well. We just push it onto the stack. Okay, so after this, if we do this for each line, if we do this for each token inside each line, we have one stack for one line, and we push that into the stack history. So for every line we generate a stack. For every line we push that stack into the stack history, and in the end we return the stack, or we set the stack history for this function. Okay, so this is how the stack generation works internally. And if we go back inside the main function, after parsing out all the functions, we have everything we need for each function, and we pass that into this write method. And this write method deals with actually printing out. So what you can see here in the standard output, or if you want to write that into a file, the actual printer deals with that. So if we look at the printer, this is, I think, this is not that interesting from an EVM or a Huff standpoint. It basically iterates over each stack history and returns these and creates these comments, right? Okay. Are you commenting stack with bottom? Okay. So Igor is asking, can I set a parameter to print out the stack from left to right or right to left? And there actually is, which was a great, actually a pull request from someone in the community. Yes, you can set it. So if you want to run this, you do cargo run, path in, path out, and then if you ignore this, you do basically left or you do right. This is how you set that. Okay, so if you want to work on this, and yeah, any help on this would be greatly appreciated. There's a number of things to be added. So the first one is add support to duplicate, dup, and swap opcode, which actually DevTooligan started working on. So there is an open pull request for this, but there's still some things to figure out. There's also, so using an iterator, this is more of a Rust thing. I think one could refactor the Lexer to use an iterator, which would be a nicer implementation. But actually the bigger or the better thing would be to remove to remove the parser or the lexer completely, and fork out the Huff lexer inside HuffRS. And a very, very big thing would be to support jumps, because supporting jumps is rather complicated, because if you take the jump or you don't take it, actually changes the stack history. So every jump will split the stack history into two separate histories, which is a bit complicated to implement. But yeah, that's basically an overview of Huff Stacker. Right. If you have any questions or comments, please let me know. Put them into the comments or raise your hands and I put you up on the stage. Okay. Okay, while we're waiting for some questions, let me... Great tool, thank you. Yeah, thank you, Igor. Would be happy. Yeah, definitely open for any contributions. Just look at the to-dos and do a pull request, basically. And I think using the Huff lexer would be a great thing to work on. The one problem is the Huff lexer. The Huff lexer doesn't give you the information, so you basically lose the information of the line number for each token, which we definitely need. But the Huff lexer doesn't need that, because if you do code generation, it doesn't matter which line the opcode is on. So what you would need to change in here is you would need to fork that and support line numbers, which I don't think would be too difficult to implement. Okay, Michael is writing something. Yeah, another thing is what I'm working on. What I'm working on for the hackathon is a Huff formatter. So the goal of this project is to automatically format Huff files, and it basically has the same. It needs the same information as Huff Stacker. So yeah, if you fork the Huff lexer, would be very useful not only for the Huff Stacker but for the Huff formatter as well, because one needs the line number there as well. Okay. So yeah, this is basically it from my side. Michael, if you don't want to type, I can put you on the stage if you want to. Maybe that's a bit easier. Just say yes or raise your hand or something. Okay. Okay, it doesn't seem like it. So yeah. Thanks again, guys, for tuning in. This is recorded, so we're going to put this up on YouTube.